Welcome back to this tutorial series on implementing numerical methods in Python, and in today's video we're going to be going over the gamma function. So the gamma function is a factorial function used commonly throughout mathematics, especially in statistical gamma type distributions. Its value is simply calculated by n-1 factorial for discrete, otherwise known as integer values of n. So let's say we have an example of n equals 4. To calculate the gamma function of 4, we simply say 4 minus 1 factorial, which is 3 factorial, which is 3 times 2 times 1, which equals 6. Now, how would you calculate the factorial of a float values or a decimal value for continuous values? So how, for example, if I wanted to say calculate the factorial of 3.5, how would you do that? You would do that through the gamma function, because also the gamma function is represented by the following integral. So here we have our equivalent. We simply take the integral from 0 to infinity of x times x raised to the z minus 1 times e to the negative x, where z is simply our n. So let me change this to n just for notation's sake. So if I wanted to say f sub 2 of 4, okay, unfortunately it doesn't give us the value or whatnot. However, we sort of see the point. So given an n, which is 4 in our previous example, would say x to the 4 minus 1 times e to the negative x, and integrate that from 0 to infinity. And we can see here we have this graph of this integral. And if we were to plot our original one for discrete, for integer values, so unfortunately I can't overlap both of these functions on the same graph, so I had to make two different graphs. So here we have our continuous integral for approximating the gamma function, and then we have our discrete gamma function value, which is simply denoted as x minus 1 factorial. And as we can see here, if I was to zoom out, we would have this for negatives, and we would have this for positives. Now we would only use this function for positives because we're dealing with real numbers, to where you can't take the factorial of a negative number. So here we have it, our curve. As we can see here, can't overlap them. However, they are the same curve. So one is for continuous, one is for discrete. And this is how we're going to approximate our gamma value. First, going to check to see, is it discrete? If it is, we're going to calculate it using this value. And if it's continuous, meaning like a float or double, some kind of decimal, then we're going to calculate it using this integral. So now let's actually implement this in Python. So now we're going to say def gamma, we're going to pass it an alpha value, where alpha simply is the same notation as n. So alpha is the same as n. Now we're going to say if the int of alpha equals the float of alpha, that means that alpha is an integer. And we're simply going to return the factorial of alpha. And now I'm going to make a helper function named factorial. Now what is a factorial? It's a quick reminder, you simply give it an integer, let's say 5, and it's going to calculate the sum, the product sum of all the values beneath 5, between 5 and 1. So it'll be 5 times 4 times 3 times 2 times 1. So we simply calculate the product of the value. And we do that by the following. We're going to say sum is equal to 1 for I in range of 1 to x. Now we're going to make our product. So let me actually name this product instead of sum. And we're simply going to return our product. So instead of this for loop is, instead of counting backwards from 5 to 1, it is going from 1 times 2 times 3 times 4 times 5. So I in range. So simply what it does is it takes I in range from 1 to 5 in this example, and it takes our product and it times it by I, where I is increasing from 1 to 5, and that's how you get the factorial. So if alpha is an integer, we return the factorial. If it's not, then we have to calculate the integral value. So here we have our integral value, and we're going to approximate using our previously defined integrate infinity function. Unfortunately, we can't use the standard stock infinity function. So in the previous videos, we've split our methods into two parts. Our stock our stock method where we pass in our functions, and then we have our calculator where we actually implement our recursive descent parser within our method. Now, unfortunately, we can't necessarily do that with the gamma function because, as we see here, the function we're integrating over is changing for each alpha value or n value we choose. So we're actually going to have to hard code this for it to even work. And on top of that, our infinity method here also requires an inverse function. So then we're going to have to define not just our function, but also the inverse of that. So we're going to have to hard code these functions for specific problems, and this is just not very good at all. So instead, from here on out, we're going to stop using functions and we're going to start using our parser. So in the previous series, we went over a recursive descent parser and how to build it for a simple calculator language, and now we're going to use that. So first things first, we're going to import our scanner and our parser. We're going to say from scanner, import scanner, from parser, import parser. And so now what we need to do is we need to make a constant known as Euler's number. So this E right here denotes Euler's number, and Euler's number is given by the following value. So 2.718, and of course this is just a truncated value of it. It goes on for infinity, just like pi. And now we're going to make our tokens. So before we do that, we're going to make our function is equal to x to the a minus 1 times e raised to the negative x power. And get our tokens from the function. So here we have our function hard-coded. And what we're going to do is we're going to make our parser. And now we're going to implement this. But before we do that, we need to add our constants. And now there's two ways to do this. We can either hard code our constants inside our parser class. So here we have our variables, and simply what we can do is we can add two new variables. We can call it e, and we can call it pi, for example. That way we can have hard-coded values and we can call them. However, the problem is if we wanted to have a variable denoted by e, we would have a mix, we would have a clash between a user-defined variable named e and Euler's number, which would be represented by e. So instead of hard-coding these constants as variables, I'm going to add them as variables outside. So as we see here, we used e and we used a. And so what I'm going to do, I'm going to say our parser dot add variable a, and we're going to pass in our alpha value. Add variable e, pass in our Euler's value. Now, granted, we wouldn't hard code a in parser. We would just hard code Euler's number in probably pi, probably denoted by pi. So instead of doing that, we're going to actually just allow the user to explicitly make these variables. So our value is simply equal to our infinity calculator. I'm going to import this real quick. So from integrate infinity, import infinity calculator. Infinity calculator, we're going to pass in our function, our parser, then our tokens, a tolerance of 1e to the negative 10, and then our a value, which is alpha. 0. So there we have it. We have our gamma function, and now let's actually test this. Before we do that, we need to return our value. So now let's actually test this. We're going to say print gamma of, let's say, 5, just to make sure our integer expression is working. So enter in function. Let me comment this out inside here. This is from our previous video. So now we run this again. There we go, 24. So that is 5 factorial. Now let's do 4.5. 51 iterations needed. So there we have it. Our approximate value is 11.6317. We needed 51 iterations for this composite Simpsons rule, and we needed 619 iterations for this composite Simpsons rule. And so now what I'm going to do is actually going to time this. So we're going to say import time, and we're going to say start is equal to time dot process time print time taken, the string value of time dot process time minus our start. So we get the process time here, and then we get the new process time after we call our gamma function, subtract the start time, and that should give how long our function took. So now we run this. So it took us 1.9 seconds to approximate this value. And we can make this faster or slower simply by changing our tolerance. So now let's make this 1 e to the negative 8. So it took shorter, 0.75, as opposed to 1.68. So we halved our time simply by lowering our tolerance. And we can do this again to, let's say, 1 e to the negative 6. And that runs extremely fast. So it all depends on what kind of tolerance level you want within your gamma value. And so for our sake, for future videos, we don't even need our gamma function to be that accurate. We just need probably the first 4 decimals. So that's exactly what we're going to use here, and it is extremely fast. So if you want our gamma function to be extremely accurate to machine precision, it's going to take longer. However, if we decrease the accuracy to only off by 1 e to the negative 4, we can get lightning fast results. And this is extremely useful. And now I'm going to compare our gamma function to the gamma function found in R. So as we stated before in the very first video of this series, of this introduction, at the very last part of section 1, or part 1, we're going to be going over a lot of functions defined in R, such as such as chi squared, q chi squared, p norm, and the gamma. So now let's actually print out some examples here. Let's go from 4, and let's make this 5.5. Let's make this 7.785. Print the gamma of 10. So let's run this. So here we have 6, 11.63, 52.34, 3,277, and 362,880. So now let's call our gamma here with 4. So we got 6, that is correct. Gamma of 4.5, 11.63173. As we can see here, that is extremely accurate. Gamma of 5.5, 52.3427. So as we see here, this is also very accurate. Gamma of 7.785, 3,277.726, and then gamma of 10. Now since 10 is an integer, you just take the factorial of it. So the impressive part of this is we've actually replicated the gamma function as found in R. So hopefully you guys have learned how to implement the gamma function, know a little bit about it and what it's used for. And in the next video, we're going to be going over the chi-square distribution. So stay tuned.